or the work done by gas or on gas. Okay, so for work done by a gas which is expanding against a constant, what it's written, okay, a constant pressure. Yes. So the constant external pressure. Meanwhile, the for work done by a gas which is expanding against a constant external pressure. What does it mean? It means that first of all, your cartridge is on this gas syringe and the piston inside the gas syringe. Okay. So this is the gas, and the force exerted by the gas, shown by the blue arrow, with as the black arrow shows the force or the force from the external pressure. All right. So, what does it mean? That the force of gas is has traveled a distance, move. All right. So, what does it mean? Basically, that the delta x shows the distance or the change in distance moved by the piston. All right. So the symbols also clarify you that F is the force exerted by external force or external pressure on piston. P is the constant external pressure. Delta X is the distance moved by piston, and A is the cross-sectional area of piston. All right. For a piston with a cross-sectional area A, the force F acting normal to it is given by F is equals to PA. Meanwhile, force is equals to pressure multiplied by area, cross-sectional area. This is the first equation. Keep this in your mind. All right. So how can you calculate the force? You can calculate the force here by the pressure, the external pressure on the particular area. All right. For a gas with pressure is equals to external pressure P, if the piston is allowed to move outward slowly by the displacement delta x, the gas will expand against the constant external pressure P, and the force of gas is equals to the force of external pressure. Understand? Okay. Okay, we have done this. The work done W by the gas against this constant pressure P is given by W is equals to F delta x, where force F is force and delta x is change in displacement. Okay. Okay. Hence, okay, wait a minute. So, all right, wait a minute. So basically, how can I write that work done is equals to PA delta x? This is because of the pressure formula. Do you know the formula for pressure? Pressure is equals to force divided by area. Area will go to multiply with pressure to find out the value. By making the subject of force, or for making the subject force, we'll be multiplying area by pressure. So from the area, or from the what we can say, from the equation, we'll be replace force by PA, which means pressure multiplied by S, pressure multiplied by cross-sectional area multiplied by delta x, means change in displacement. Now just focus that AX, meanwhile area multiplied by height. Obviously distance is height. All right. Is this a formula for volume? I mean, I can say that this is the change in volume. For volume, you write AH. Meanwhile, area multiplied by height. So from this equation again, which I have made from F is equals to, sorry, W is equals to Fx. I'm trying to say obviously the W as F. I do not know, but W is equals to Fx. Near the F I replaced by the pressure formula, in the which I make the force subject, and then I find out the PA. All right, or I find out the force, and then I made the PAX, and then from A delta x, I find out that this is volume. For volume, we find out AX. Alright, so I'll just replace P delta V. What does it mean? Hence, when a gas expands with a change in volume, delta volume, or delta V against constant pressure P, work done by the gas is given W is equals to P delta V, where W is work done in joules, P is external pressure by in pascals, obviously, and delta volume is the change in volume of the gas, which is meter cube. Alright? And yes, final minus initial is equals to change in volume. That is understandable. Okay. If pressure is constant, work done is given by W is equals to P V2 minus V1. I mean change in pressure. That's nothing new. Alright. Okay, and this is the graph. Okay, this is the graph. So this graph shows the work done. Now we see from what else shows you the work done? From the previous live session, we have already discussed that the force displacement graph shows you that this area under the displacement and force graph shows you work done. Similarly, wherever the pressure against volume graph is shown to you, it means that area under the pressure volume graph is work done. Alright, from where you will derive. Also remember how I derived this equation W is equals to P delta V from W is equals to F delta X. Alright, there's a great derivation and it obviously comes in the paper. So when gas expands and when gas is compressed, examiner always asks from you whenever the gas expands or whenever the gas compresses, none of the third scenarios given to you. There are only two scenarios. You're going to focus on these two scenarios. That when the piston moves, where the piston moves when the gas expands. Obviously, when the gas is expanding inside the syringe, the piston will move outward. Obviously, when it's compressing, it means that we are applying the force to the piston to just make or just move inward to compress the gas. All right. Force exerted by gas on surrounding and displacement moved in the same direction. When the gas expands, the force exerted by gas on surrounding and displacement move is in the same direction. Now, when it is compressed, it moves into the opposite direction. Direction matters. You're required to focus on this, okay? Work done by gas on surrounding. When the gas expand, now this is very important. When the gas expand, so the work done is positive. Okay, and when the gas is compressed, then the negative work done is applied. I mean work done by gas on surrounding. Work done by gas on surrounding is positive when gas expand. Yeah, I'm not saying that it is on the gas. Work done by surrounding on gas. What is the effect of work done by surrounding on gas? Is when the gas expand, the work done is negative. This is because the work done by surrounding on gas. It means that obviously when it's expanding, so the work done by surrounding on gas is negative, and when it is compressed, it's positive. But by gas on surrounding, it is positive when it expands and it's negative when it compressed. Alright? So work done by gas on surrounding and work done by surrounding on gas. Yes. Okay, at last we say a gas does work on surrounding when the gas expand and surrounding do work on gas when the gas compressed. That's understandable and that's very easier. That we are basically doing the work on the gas to compress it. Okay, so the surrounding do work on gas when we are required to compress it, and when we are required to just when it expand by itself, it means that it is doing work. Okay, so it is doing work then. All right, so try to solve it, and there is a question for you candidates. Yes, there is a question. A gas in a cylinder is kept at a constant pressure of 1.1 multiplied by 10 raised to power 5 pascals. The gas is heated and expanded by 25 centimeter cube. Now the volume is given to you and the pressure is given to you. Calculate the work done by the gas. By the gas. mean, is it negative or it would be negative or positive? I mean to say, if you know it, you know that the value coming is in the negative or in the positive. It's not coming, so you just apply the negative or positive sign. That's not an issue. Okay, the conversion is one of the important thing in your AS. 1 centimeter is equals to 10 raised to power negative 2 meter. Okay, and similarly, 1 centimeter cube is equals to 10 per raised to power negative 6 meter cube. Okay, after the conversion, we got the value of 25. Okay, we got the value of 25 multiplied by 10 raised to power negative 6. All right. So this is for which we are converting centimeter cube to meter cube in the formula. Plus the pressure will remain the same. 1.1 multiplied by 10 raised to power 5, and the answer is in positive 2.75 joules. It is positive. If it is positive, it means that it is the work done by the gas, all right, on the surrounding. As you can see this diagram, which I show you in the beginning of the chapter, all right. Okay, so derive from equations of motion kinetic energy. Now we are going to just focus on the kinetic energy. In this chapter of work done and energy, we are going to focus on some energies such as kinetic energy is one of them. Okay, so the kinetic energy Ke, basically we represent kinetic energy as Ke or E from this formula. E and the small as very small, you can see below K. Okay, the positive scalar quantity. It means this does not have any direction, due to which it is scalar. That represents the energy associated with the body due to its motion. Means whenever there is a motion, there may be a kinetic energy. Alright. It is equal to the work done by a resultant force in accelerating the body from rest to an instantaneous speed v. Alright. You must require to derive it formula. Half mv square, where the m is mass, which is in kilogram, and the velocity is in meter per second. The SI unit for kinetic energy. What is the SI unit for kinetic energy? Although it's written here, but I was asking from you that just let me know. Joules, and from the name you can also determine that this is an energy. It means that it must have the SI unit joule. All right. Derived from motion kinetic energy. Derived from the equations. Okay. Kinetic energy is equals to half mv square. Okay. Now just see the mass from the initial velocity have some net force, okay, which has traveled a distance s. All right, body initially at rest means the initial velocity must be zero. Work done by net force is change in kinetic energy of body. What does it mean? As I told you in the starting of this chapter in the previous live session that work done is equals to change in energy. What is kinetic energy? Kinetic energy is the energy. Obviously, it means that this work done by the net force is equals to change in kinetic energy of the body. All right. So now, how you're required to just derive the formula for kinetic energy is the work done. Again, work done. Everything of work done. Okay. So work done is equals to change in kinetic energy. You do not know the formula for kinetic energy. You just forget that you do not know the formula for kinetic energy, and you're required to just derive it. Okay. For work done, the net force multiplied by displacement. This was the formula for work done. Yes. Okay. From the force, what is the formula for force? Ma, mass multiplied by acceleration. So mass is equals to kinetic energy, means mass multiplied by acceleration multiplied by displacement is equals to kinetic energy. Now we are required to derive the formula. I'm using the equation from the accelerated motion in which we have discussed from the kinematics live stream. I required to just focus, go there and just watch. If you do not know, v square is equals to 2 u square plus 2as. I'll derive the formula for as. So what will be happening is that as will go there. All right. And wait a minute. Yes. Yes. As will go there and will be multiplied by v square. while the v square will become there. Okay, okay, wait a minute. No, 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 wait a minute. The u square is multiplying by 2as. It will go there and minus, subtract, obviously, with will with the final velocity square. Okay, and the 2 at this position will be divided from there. It means that v2 minus u2 upon 2, and that's what I'm trying to say. Okay, now from the mass multiply by acceleration multiply by distance, you'll be keeping, what you're trying to do is that you'll be just do the simple thing is that you're keeping the value of as, means acceleration multiplied by distance or displacement, and you're just using the value half mv square minus half m and u square is equals to kinetic energy. But for u, what is the value for u? Initial velocity. The body is at the rest, means initial velocity is 0. So the answer must be 0. Okay. So only one equation left. That's the formula. Kinetic energy is equal to half mv square. Also practice more past papers so that you can understand it. Okay. Note. Kinetic energy is a scalar quantity and has the same units as work. Meanwhile, joule. Work done by net force is equal to change in kinetic energy of body. Okay, w or work done is equals to half mv square minus half mu square. Understand? Okay, sample problem 1, solve it. Okay, and that's one of the easiest question. A car of mass 800 kilogram and moving, okay, and moving at 30 meter per second along a horizontal road is brought to rest by a constant retarding force of 5000 Newton. Calculate the distance traveled by the car in coming to rest. Okay. Using the kinetic equation. Can you use the kinetic equations? You can use the kinetic equations or the accelerated motion equation. V square is equals to as. Insert the values and you'll be getting the answer as the same. You can try another way. Using work done is equals to change in kinetic energy. W is equals to half mv square minus half mu square. Insert the values and you'll be getting the answer. So both options are valid, both methods are valid, and you can see that the answer are same. Okay. Energy in different forms. Okay. It's conversion and conservation, and apply the principle of energy conservation to simple examples. Okay. So types of energy and their resources. For mechanical, okay, mechanical is not right for means it's not for your AS level. Okay, so for kinetic energy, energy possesses by all objects in motion, gravitational potential energy. It's not new to you if you are from O levels. Okay, so energy possesses by an object by virtue of its position in a gravitational field. For example, from waterfall and from raised object. Elastic potential energy, energy possessed by an object by virtue of its state of deformation. We'll be discussing later in the next chapter, such as compressed and or stretched springs, a band diving board, the stretched elastic band of a catapult. We'll be discussing it later. Electrical due to the charge or current, chemical energy possessed by a fuel, okay, nuclear, radiant and internally. Okay, then just that. Renewable and non-renewable energies. Okay, so renewable, sources of energy are those that can be replaced okay. Wait a minute, is it part of your syllabus? Okay, okay. So moving towards the gravitational potential and energy, or as you know, there's a simple definitions of renewable and non-renewable energies, but that's not the part of our AS syllabus. Okay, so gravitational potential energy, electrical potential energy, and elastic potential energy. Potential energy is the energy possessed by a system by which of the relative positions of its component parts. Gravitational potential energy (GPE) is associated with the interaction between. Okay. Alright, so the gravitational potential energy Gp is associated with the interaction between bodies due to their masses. Electrical potential energy is associated with the interaction between bodies due to the electric charges. And elastic potential energy is possessed by an object due to its state of deformation. So, till that it's here. I'll see you in the next video. Till that, take care.